Okay, so now on this sheet, harder problems with acceleration. We have 3, 5, and 6 to do. So number 3 says, balls roll down inclined planes because of the pull of gravity. They accelerate down the plane just as they do when falling through the air, except the value for acceleration is not 9.81 meters per second squared, right? That's only if they're falling straight down. But on a plane, they're not falling straight down, they're rolling. Okay, so we have up here, and so for a given, how fast they accelerate is dependent upon the angle. So as long as the angle doesn't change, the acceleration of the ball on the incline won't be any different. So a ball is released from rest. So this is ball 1. Okay, so our givens for ball 1, released from rest. So VI is 0. A ball is released from rest at the top of an incline that's 18 meters long. So it's going to roll down the incline 18 meters. And it rolls to the bottom in 3 seconds. Delta T, 3 seconds. At the same time, at the same instant the first ball is released, a second ball is rolled up the incline from the bottom. So we have ball 2 down here. And it's rolled up. So it's given some VI that we don't know. And it's going to go up until it stops somewhere here. And then it's going to turn around and come back. Okay, so for ball 2, we don't know the VI. We know it's not 0. Rolled up the incline. The second ball is supposed to roll up the incline part way and then stop, roll back down to the bottom again, and arrive back at the bottom at exactly the same time as the first ball. So its total T needs to be 3 seconds as well. It's not going to make it halfway up, or at least you can't assume that. So, but what we do know is that the A, whatever the A is for ball 1, that will also be the A for ball 2. So we can find the A for ball 1, because we know delta D1 is equal to VI delta T plus 1/2 A delta T squared. This goes to 0, rearrange for A, multiply both sides by 2, divide by T squared. So 2 times 18 should be about 36, divided by 3 seconds squared, which is 9. 36 divided by 9, A is 4 meters per second squared, which means the A for ball 2 is 4 meters per second squared. Now, what else do we know about ball 2? We know it goes up part way and then stops. So if we look at just the up piece, then we don't know the VI, but we know the VF is 0. And we know the A will be 4 meters per second squared down the incline. And the time has to be half the time, because however long it takes to go up, it needs that long to come back. And if it has 3 seconds in total, then it must be going up for 1.5 and down for 1.5. So from that, we can find our VI. We can do A is equal to VF minus VI over delta T. So A delta T is equal to VF minus VI. And if we're looking at just the up, the VF goes to 0. And so then VI will equal negative A delta T. Negative, and our A has to go in as -2 because it's going down the incline. Or if you wanted to call down the incline positive, because we did here, so we could put our 4 meters per second squared in here, times 1.5 seconds, and you'll end up getting a VI of -6 meters per second, where the negative means opposite the A was down, this is going to be up. Okay? So that was part 2. Part 3, how far up the incline did it go? So now you're looking for delta D2, and it'll be VI delta T, 1/2 A delta T squared. So delta D squared equals. So do you want to call up positive now? Should we switch? So if we did, this will be 6 meters per second. It was going up for 1.5 seconds. Plus 1/2, negative, because that's down, 4 meters per second squared, 1.5 seconds squared. delta D2 is equal to, that will be 9 meters, 2.25 times 2, 4.5 meters, negative because of the 4. Delta D2 is equal to 4.5 meters, which is up the incline. Had you wanted to keep it the same as above and wanted to call down the incline positive, then your 6 meters per second would go in as a negative, your 4 would go in as positive, your 9 would end up being negative, your 4.5 here positive. It would give you a negative here, and you would say, negative was up the incline. Okay, so it doesn't matter which way you call positive, just keep track of it. Number 5 says, a rock is dropped from a bridge that's 30 meters above the water surface. So here's the bridge, here's the water, here's the bottom. So this distance, delta D, is 30 meters. It's dropped, which means VI is 0. A is 9.81 meters per second squared. Delta D is going down, A is going down. It slows down instantly upon hitting the water to a quarter its speed. What speed is its speed? The speed it was going just before it hit the water. We don't know what that is yet, but we know the speed in the water is 1/4 of that. And then it says, and then it falls, it sinks to the bottom at a constant speed. So 1/4, that becomes your VAV. Okay? If it takes 4 seconds from the time it was dropped until it hits the bottom, so the whole thing is 4 seconds. So we don't know what delta T1 is, but once we find it, delta T2 will be 4 seconds minus that. Okay? And so then the question wants to know, what is the depth of the water? Delta D. Okay? So if we can find our T1, we'll have our T2. If we can find our VF, we'll have our VAV. So start up here. So first above. We can get our T1 by doing delta D is equal to VI delta T, 1/2 A delta T squared. The VI is 0. So delta D1 is equal to 1/2 A delta T squared. We're trying to solve for T, so multiply both sides by 2 and divide by A. So 2 times 30, and everything's going down, so we can just call down negative, divided by 9.81 meters per second squared. And remember, that will be a T squared, and you will need to take the square root. And when you do, you get 2.4731 seconds. So that's the time above the water. Now you can also find the VF above the water, because you know VF squared is equal to VI squared plus 2A delta D. You could also use A equals VF minus VI over delta T. VI is 0, so VF squared is equal to 2 times 9.81 meters per second squared times 30 meters. The advantage of doing this one is it's not dependent on the time. And then take the square root and you get 24.261 meters per second. Okay, so now that we have these two things, we can find our VAV. It's just 1/4 of 24.261 meters per second. So our VAV for in the water should be something like 6.065 meters per second. And we can find our delta T2. It's 4 seconds minus the 2.4731 seconds we found above. So our T2 should be 1.5269 seconds. And then with that, we can get our delta D, because VAV is equal to delta D over delta T. So delta D is equal to VAV times delta T. Delta D is equal to 6.065 meters per second, 1.5269 seconds. Multiply them together and get the depth to be 9.261 meters. Okay? So that is number 5 and number 3. Next video we'll do number 6.